Hello everyone. It's that time of year again. Time for Advent of Code. I say that time of year as if it were like a thing I do all the time. This is only my second year recording Advent of Code. But if you guys watched it last year, I hope that you enjoyed it, and we are back this year. But as you can see, we are a little bit behind. It's this programming puzzle thing that Eric Wastel, who calls himself Topaz, puts together every December, presenting you with a fun Christmas-themed programming puzzle every day from December 1st through December 25th. And you can compete on leaderboards and try to complete the problems as fast as possible. Totally not my jam at all, but there are people who have a lot of fun with that. I just use it as a way to do some fun exercises and in practicing whatever it is that I feel like practicing. Last year I programmed in Python because I thought I would be using some more Python at work, and I knew the basics but not really how to write good programs. And so I practiced especially not just the language Python but also writing kind of object-oriented Python, whereas I've been in a much more functional programming kind of place for the last several years. So that was what I wanted to practice last year. This year, I decided I would rather just get back to doing more functional programming. I kind of miss it. And so I will be doing this year's exercises in Haskell, a purely functional, statically typed is the word I'm looking for. Statically typed language, and I'll try to give you guys kind of like a crash course in Haskell, but I'm definitely not going to be telling you guys enough to be like a full tutorial. So if it's all totally foreign to you, you may be a bit lost, but there's plenty of things you can go read. For example, the excellent online free book, Learn You a Haskell for Great Good, is a bit silly, but definitely has some great material. So it's a fine way to learn to program in Haskell if you need to do that. Needless to say, if you're watching this and you're like, I don't care at all about programming, when do you get to the good part? Like, haha, gotcha, that's the good part. If you don't care about programming, I suggest you not watch the rest of this video or any other videos in this playlist, because that's what they're going to be all about. With that, I guess, let's read puzzle number 1. By the way, this is take 2 for me. I read this whole thing and told you guys a little bit more about Haskell and what I wanted to practice this year, and then I accidentally cut off the recording and started talking about other stuff, and I figured let's just start over. So anyway, day 1, inverse CAPTCHA. And so first they're going to set up for us the theme of the whole month of puzzles, and then they'll tell us about this specific puzzle. Day 1, inverse CAPTCHA. The night before Christmas, one of Santa's elves calls you in a panic. The printer's broken. We can't print the naughty or nice list. By the time you make it to Subbasement 17, there are only a few minutes until midnight. We have a big problem, she says. There must be almost 50 bugs in this system, but nothing else can print the list. Stand in this square, quick. There's no time to explain. If you can convince them to pay you in stars, you'll be able to... She pulls a lever and the world goes blurry. When your eyes can focus again, everything seems a lot more pixelated than before. She must have sent you inside the computer. You check the system clock. 25 milliseconds until midnight. With that much time, you should be able to collect all 50 stars by December 25th. Collect stars by solving puzzles. 2 puzzles will be made available on each day, millisecond, in the Advent calendar. The second puzzle is unlocked when you complete the first. Oh, really? I thought last year you could do them in any order. That's interesting. Each puzzle grants 1 star. Good luck. Okay, so there was something that while I was reading this, I realized I wanted to tell you guys, but I don't remember what it was. Oh well. So now we're going to learn about this first puzzle. Oh right, it's all cutesy Christmas themed stuff. If that particularly offends you, sorry, I guess. Not much I can do. You can leave, I guess, or you can sort of suspend your disbelief and pretend it's not about Christmas, or you can just sort of, if hopefully it doesn't offend you and you enjoy all this silly Christmas theming stuff, but it definitely is both silly and Christmassy. You're standing in a room with digitization quarantine written in LEDs along one wall. The only door is locked, but includes a small interface. Why does it interface? I don't understand why how this title is like. Is it the title of the interface, or is it what's written on the interface? I don't know. Restricted area. Strictly no digitized users allowed. And we are digitized users, of course, so we're going to have to break in. It goes on to explain that you may only leave by solving a CAPTCHA to prove you're not a human. Apparently, you only get 1 millisecond to solve the CAPTCHA. Too fast for a normal human, but it feels like hours to you. Because, of course, we're digitized. The CAPTCHA requires you to review a sequence of digits, your puzzle input, and find the sum of all digits that match the next digit in the list. The list is circular, so the digit after the last digit is the first digit in the list. So they give a few examples here. 1122, this one matches the next digit, so it counts, but this one does not match the next digit, so it doesn't count. Likewise, this 2 matches the next digit, so it counts, and this 2 doesn't match this 1, so it doesn't count. But here, all 4 ones count, because they each are the same as the next thing, and so we add them all together. So a nice thing about Advent of Code is that it's a programming puzzle thing, but Eric doesn't need to run any programs. You can write in any language you want because he's just grading you based on your answer. And so each participant gets a different, or anyway, there's a set. I don't know if they're all distinct, but typically you will not get the same puzzle inputs as anybody else in particular. And they're large inputs, too much for a human to do by hand, typically. But small enough that even on a kind of crummy computer, you should be able to do it in a reasonable amount of time with a reasonable algorithm. So I've already, in fact, grabbed my input and saved it on my programming machine. Which brings me, actually, before we get into solving this problem, to the other thing that I wanted to practice this year. I'm programming on my Windows desktop this year, whereas previously I was programming on a MacBook, which is sort of the MacBook is a much more programming friendly environment if you are used to being on Unix. Of course, many people program in Windows, and I'm sure that is lovely. I don't really know how. Like, long ago, I used Eclipse and wrote Java and stuff, but for several, probably not 10 years, but close to 10 years, I've been doing basically just Unixy stuff for a long time. However, I have this great recording set up for my Windows computer. What to do? Of course, SSH to the rescue. So I have a Linux machine just sort of lying around that I have access to do whatever I want with. And so I'm just going to log into that machine and try one thing. Of course, SSH is not something I need to practice. I've done that a lot, right? But what I want to try getting better at is my window management. It's something that I'm pretty crummy at. I just make new windows at the Windows level or the Linux level or whatever. The window manager level. And I'll have 10 console windows open, and keeping track of which one goes where is super hard. And I can't have more than one on the screen very easily. And so I wanted to practice using tmux to manage all of my console terminals in a session in a more manageable way. So a restriction I am putting on myself for this year's solutions is that I should have exactly one SSH session to this remote server. This should not be terribly burdensome because I don't really want to do many things there, right? I want to run Emacs and I want to run a shell, and that's it. And really, if I wanted to, I could run the shell inside of Emacs and not need to use tmux at all. But I want to practice using tmux, so we're going to do that. And so tmux is the terminal multiplexer. It lets you run multiple different programs at the same time and display them, be able to switch between them from within a single terminal. So for example, I have an Emacs window open in this same session, and I can switch between them with a couple keystrokes. If I were so inclined, I could open another terminal and switch between them like so. I don't really anticipate wanting to do that because I just kind of want to run my programs in this window, and that's all I need to do. But hey, I can switch things if I need to. Additionally, I haven't really used Haskell for any big projects. Like literally Advent of Code last year was the biggest projects I used Haskell for. So really just small stuff. And so I have a habit of just using sort of like Haskell files lying by themselves on the file system, not part of any project. And that's like, I guess, not really a good habit. And so I'm trying to get into the practice of using Stack to manage my Haskell projects. So I've gone ahead and created a Haskell Stack project for each day of Advent of Code. And a very simple one. And I know how to run like a shell or a GHCI, a REPL, that's the word. And I know how to run a program from Stack. And if I need to add a dependency, well, we'll go look that up, I guess. I don't know how. I've also, by the way, hang on, shouldn't that have made you guys be able to see this? What's happening? Did I get my... Oh, no, I just forgot the number. Okay, here we go. I wanted to point out I also have a Tmux cheat sheet open here in case like I forget something that I can't look up from within Tmux itself, but I should be able to look stuff up from Tmux itself as well. Okay, great. So I've already downloaded my puzzle input and stored it in input.txt. 2 kilobytes of just like numbers. There it is. Fine. So with that, it's sort of time to start writing a program, but not really, because I have to tell you guys a little bit about Haskell first. So as I mentioned, I think, as I said, this is my second take, so I don't remember what I've already told you guys. Haskell is a functional programming language. It is, in fact, a purely functional programming language, which is more than most functional programming languages. It is to say that you may never modify any values. You know, if we say x is 5, then x is 5 forever, and that's just it. It's never going to be 6. Objects, sort of like Haskell has things that are kind of like objects. You know, it can make data types that are composites of other data types. You can sort of attach functions to those things, but you can't modify them. You can't say, you know, person.setName Steve. Not possible. Can't be done. Which seems very restrictive if you're used to thinking in terms of Java or something like that, where you mutate stuff all of the time. But it turns out that with the power of recursion, a lot of this stuff turns out to not actually be recursion and laziness, I guess I should say. A lot of this stuff, it turns out not to be as big a restriction as you might think. And I've been doing, as I think I said, functional programming for the last, like, I don't know, 8 years or something. And so it all feels quite natural to me, but it will feel unnatural if you are not used to it. So I'll try to explain what all is going on here. First, of course, we just have module main. We're defining the name of our module is to be main, as it should be for any simple program. This is what gets run. We'll have probably just one module for most of our programs. And Haskell's syntax is kind of driven to look a lot like math. So, you know, you might say, suppose that X is a sphere where the surface of the sphere is blah, blah, blah. And so Haskell uses where in a sort of similar way. You say, suppose that main is a module where main is, and you know, like that. It's sort of, you can read it that way if you want, or you can just like treat it as arbitrary words that you have to type. So I'll skip over this line for a second and look at this. Here is where we define main, the function that will be called when we run our program. We define a value in Haskell by just writing its name and then an equal sign. We say, here is what this value is equal to. And because nothing ever mutates or changes, this is actually equality. It is not an assignment, right? We're saying you could replace, anytime someone writes the word main, they could instead write do _line hello world. Those two things are the same, is what this equal sign means. This gets you sort of referential transparency, equational reasoning. There's all this kind of cool stuff that you can... It helps to not have to worry about anything ever being reassigned. You can reason about your program better. So we say main equals do, where do is this construct that like is actually way more subtle than it might look at first. But in most of our early programs, do will just be like a way to define a multi-line action. And in this case, our multi-line action is just a single line, which is putzerline of hello world. Where putzerline is a function that is given a string and prints that string to the console. Something that might surprise you here is that we don't have any parentheses. Haskell, as a functional language, thinks that calling functions is so important that they want the syntax for it to be as minimal as possible. And so to call a function, you just write the function's name and then the argument, and that's it. If we had multiple arguments, such as what is a, I can't even think of an IO function that that wants multiple arguments, but you know, map, for example, map tail of ABC DEF or something like that. If a function takes two arguments, like map does, map takes a function to call and a list of items to call that function on, you just put them all separated by spaces, and it sort of works out by magic, and maybe we'll talk later about like how it knows that map takes two arguments. But it sort of is implicitly parenthesized as, you know what? Doesn't matter. I'm not telling you about implicit parentheses yet. So we've defined main here to be this thing that calls putzerline hello world, but since Haskell is all about types, we also, it is a matter of good practice, but not required, to tell Haskell what type you think your values should have. And so here we say main has the type IO unit, where unit is these two parentheses. And again, we'll get later to what unit is. It just sort of means, you know, nothing. You know, main is an IO value that returns nothing. Roughly is how we can parse this line. Main is a value which has the type of an IO value which returns nothing. Sort of like that. And we can go switch over to our console window, and we should be able to say stack run GHC. Does this work? No. I guess stack run? Stack help. God, I don't know how to use stack. Stack help. I know one thing I could do, but stack run GHC. Stack exec is not quite what I want. Stack, okay. Alright, well, we probably just, I mean, I know what I can do is stack run GHC. I keep trying to tab complete that, and it doesn't work, and I wish it did. We can say that, and it goes, hello world. So we did it. We've written a Haskell program, hooray. But it's not a very interesting one, right? So now we want to write something that will actually solve our problem. And I plan for most of these puzzles not to do any file I/O in Haskell at all, which is, you might say, how could you do such a thing? Your input is in files. So of course I could just paste it into the source file, but I find that quite tacky. What I will do instead is use the shell to redirect the input of my Haskell program to be reading that file. And it is quite convenient in Haskell to work with standard input. It's so easy. Easier than, I don't know, like say Python, or especially, God help us, Java, right? There's a function in Haskell called interact. Oh, I meant to install... Oh, I have Intero mode. Amazing. All right. Well, we may or may not. GHC works for up to 8.0.1, but not higher. All right. Well, forget it. Well, I'll figure out Intero mode for some future episode. Just kill this buffer. We won't use Intero mode. Do I have Haskell mode though? Oh, I'm already in Haskell mode. Okay, great. So there's this function in Haskell called interact. And interact is this incredible function which, here, I'll write out the type for you. Interact, in principle, we should be looking up this type, but, you know, I know it, so. Oh, no, I don't want to do any of that. I accidentally typed some weird something. Intero is not installed. Get out of here, Intero. Oh my god, how do I make Intero stop? Installing, yes. If you don't want Intero... Oh, just keep this buffer around. Alright, so we'll just hide this buffer instead of killing it. Fine. So this is the type of interact. Now, we haven't seen arrows before. What are all these arrows about? An arrow is a function which takes as input the thing on the left and produces as output the thing on the right. So let's look first at this part. String to string. This is a type that means a function taking a string as input and producing a string as output. Pretty simple. Interact takes such a function as its first input. This is all about, like, remember, Haskell's a functional language. It loves functions. And so most modern high-level languages can do this kind of thing too, where, you know, you take a function as an input or whatever. But Haskell does it pervasively all over the place, and so it's sort of best to get comfortable with that. So interact takes a function from string to string and produces as output a value of IO unit. And what it does is basically it reads all of standard input into a lazy string, feeds that to your function, and takes the result out as a lazy string and writes that to the terminal. So we'll make this a comment. We don't actually want to redefine interact. An identity is, well, another kind of new and surprising type that may not be immediately apparent to you. What's the deal with identity? This is how we pronounce ID. It is a function that takes a value of some type A. So this is a generic type, much like in Java how you might have, you know, a list of A. Here in Haskell we can have just an A. It takes a value of any type and returns a value of that same type. And it turns out there's only one possible implementation of this function, which is to just return the input as the output. And so this is sort of a boring function, right? Like, why would you ever define identity? Well, it turns out to be really useful for passing to other functions, basically, right? Interact takes a function from string to string, reads standard input and writes it to standard output. Okay. Calls the function and writes that to standard output. Identity says just return the input. And so it turns out if you write the function interact identity, you've actually written the shell program cat, more or less. I mean, a very simple version of cat. And this is not at all what we're trying to do for Advent of Code today, but since today is sort of our crash course day, I figured we may as well give this a go and show you. If we now run GHC through, and we pipe its input, input.txt, it reads that file and produces it as output. Pretty cool, huh? Not useful, but it's like, try writing that program in any other language. And also consider that, like, all of these lines are optional, right? You could just write this, and that's cat, right? I think that's pretty cool. But of course, we don't want to write cat today. What we want is to write interact with a different function. And the function we're going to write is something called part1. Is a string to string, right? So that's a thing we could do. We could say, I'm calling it part 1 because Advent of Code always has 2 parts to the puzzle for every day, and I anticipate there being a part 2. But I'm actually not going to do this. I'm going to have part 1 be a string to int that returns an integer, and now interact won't work. If we were to run this program through the compiler, it would say, this is illegal. Interact wants a function from string to string. You're giving me a function from string to int. That's illegal. I will not compile your program. And that's correct. It wouldn't work even if we could somehow compile it, so we're glad to find that out right away. But what I'm going to do instead is call interact on show and part1. So show is a function that takes some value and converts it to a string. And this dot is a function composition operator. It says do the thing on the right and then call the thing on the left with that value. So we had the function, if we just look at this, interact part 1, remember interact takes a function, and part 1 is a function from string to int, so this is illegal. But show composed with part 1 is a function from string to string, because after we've called part 1 and gotten an int, we'll call show on that and get a string. So we've sort of handled all of the I/O, and this is a pattern that I find very, very useful for Advent of code, is just to find main as interact of show composed with do all the interesting stuff, basically. So, okay, now we need to write the function part 1. So what do we want to do exactly here? The first thing is probably to convert our input string from a list of values to a list of pairs of values, where the first one is the first thing in the list and the next is the thing after it. So let's write, get out of here. Actually, you know what? Let's put a parse in here, because I bet that we'll want to parse this into list of, we'll call it pairs, not parse. List of tuple of char and char. So char is character here, and these parentheses mean a pair, like a single char and another single char. This means a list of that thing. So pairs is going to be a function that takes a string, the whole input, and produces... Actually, I wonder what's going to happen with the new line in interact. I don't know. Our file has a new line in it, and I'm not sure how interact works with that. Does it keep the last one, the new line character? I bet it does, and we're going to have to fix that later. Okay, but anyway, so pairs takes a string and returns a list of pairs of characters. And already, I hope, it's a little bit apparent like that the Haskell type system is pretty expressive and concise. A list of pair of characters is like sort of a complicated thing, and it's not so easy to define in as few tokens in, say, Java, where like, yeah, there are libraries that have pairs, but people would rather you didn't use them, and like... Anyway, Haskell is a lot about composing types together rather than building new types for everything. Okay, great. So we can write pairs. It's not that hard. Pairs of s equals. So remember that when to call a function, you just write the function followed by its arguments. Likewise, to define a function, you do the same thing. Because remember that this equals is saying the thing on the left is the same as the thing on the right. So let's say we wanted to just write like this. It's illegal, let's suppose. Equals 10. We're saying that anytime you write pairs of s, you could instead write 10. So that's why the syntax exists that way, and it's very nice to have calling functions be concise. You hate to have to spend a lot of tokens on doing that because you're calling functions all the time, and you don't want to add syntactic noise for it. Anyway, so pairs of s, we'll probably write to zip s with tail of s plus of head of s, I suppose? Yeah, it's a bit tacky, but it should work. So zip, I've already, now here's 3 new dang functions. What are zip, tail, and head? And what's plus plus? So zip is we'll get to zip later. Head takes a list of things and returns the first thing. Easy enough. Tail takes a list of things and returns a list of everything but the first thing. This would be expensive if lists were arrays, but actually lists are like linked lists, and so this is very cheap. Plus plus is how you concatenate lists. And so by taking all but the first item of the list and then concatenating it with the singleton list containing the first thing, we sort of moved the first item to the end, but otherwise left the list unchanged. Zip takes two lists and produces a list of pairs of items from each list. The first item, one item from the first list, one item from the second list, and so on. And so in this way, we get a list of each item in the first list and its next sibling, and handling all the wraparound. Great. So isn't that lovely? Now, if we want, notice I've left part 1 as undefined. If we tried to run this program, that would break, of course. But we should be able to write stack gc source input source main. So it's actually broken. I broke it. Why? Oh, of course. So it is telling me there was an error at line 10 that it found a pair of characters where it expected just a single character when we tried to compose together the functions part1 and pairs. This is a big compiler message, and it can be a little bit imposing to read if you don't know what you're looking for. But actually, it's super informative and quite helpful. So basically, it's just saying, well, look, pairs produces a list of pairs of characters, and part1 just wants a string as input, so you can't really compose those two. Well, yeah, you're right. We shouldn't. I don't want to anymore. I changed the type that we were passing to part1 and forgot to update the type signature. And Haskell's type inferencer figured out this is not going to work. So let's try that again. There we go. So it compiled now. But if we run it, of course, it'll break. Undefined. So fine. Now we just need to define part1. So I think that what I will do is I will write part1 of p's, I guess, is equal to the sum of what? X, where AB is... So we're writing here a list comprehension. So we'll take p's. So for each item in p's, we will consider one at a time and destructure them into the two numbers a and b. And furthermore, we will only consider items where a is equal to b. This shouldn't be x, it should be a. So this is like a lot of new syntax, of course. List comprehensions are sort of noisy, new stuff to learn. Haskell has, I have to say, Haskell has a fairly large amount of syntax for doing fairly basic stuff. And so there's sort of a lot to learn, and it's hard for me to cover all of it for you, sadly. But basically, a nice thing that you can do in languages like Haskell is when you have a value that is, it has what's called pattern matching, right? So we have p's, which contains, actually, let me show you. We could write pair. We could say for each item in p's, call that pair, and then we could break apart. We could break apart the values in pairs into their first and second, or we could say, hey, pair, what is your first item? What is your second item? And compare them like so. But Haskell has this powerful pattern matching feature, which allows you to, instead of giving a thing a name, describe how to split it up into multiple things with names. And it's actually even more powerful than that, and we'll probably get to it in some future puzzle. But, so we say for each pair AB in the input p's, where it is the case that A is equal to B, only in that case produce A as output. And so this whole thing will take in a list of pairs of characters. I already see that this is not going to work, but that's fine. So we're taking in a list of pairs of characters and producing a list of characters, single characters, where the second character in the pair met the requirements. But you can't add up characters and get ints. That's not how it works. So what I need to do now is look up Google. Well, let's just look up Google, shall we? Here we go. You guys can... There we go. Now you can look. So I want to find Google. It's amazing. I love Google. Haskell has, because it has all these like strong types, you can actually like, if you don't know a function's name, you can search by type and like find useful functions. So I'm like, I have a character and I want an int. Like, how do I get it? And here it is. There's a function, digit to int. Convert a single digit char to the corresponding int. This function fails unless its argument satisfies its hex digit, blah, blah, blah. Okay, great. So that's all we wanted. And instead of a here, we'll write digit to int of a. And I bet we actually need to import that from data.char. Import data.char digit to int. How about now? Will this compile still? Did I break it yet? It didn't. I didn't break it, and it did compile. Amazing. So let's try, I guess, running it. What happens? 1080. Okay. This makes me a little bit suspicious. Let me try something here. Stack GHCI, please. So this is the Haskell REPL. And so I mentioned I wasn't sure what interact would do with the new line at the end of our file. And really, I'm pretty sure it'll actually include the new line, which means it won't work. The last value in our input will... Well, wait. Oh, I see. I was thinking... let me show you. I was thinking, like, wait, if there's an extra new line in our input, shouldn't digit to int have broken on it? But no, because we never call digit to int on values that are not matching something on the left or right of them. And the new line, of course, didn't match anything, so this all still makes sense. Okay, what I wanted to do was write... how would I even test this? I guess what I wanted to do is... what is lines of ABC/n? Is this single? Okay. So unlines.lines of ABC/n would actually... No, it puts it back. Okay. Is there... what functions, Google, are there from string? Is there like a way I can just remove a trailing... There's something called like chomp or something? Base, please. Lines, words, unlines, tail. More results, please. There's got to be something in here, right? I don't actually see one. Okay. Because I think we have a new line in our string and we need to get rid of it. So actually, though, that's pretty easy for us to fix ourselves. We'll define a function called chomp, which sounds kind of like a Perl thing, I guess. Chomp is a function... What am I doing? Stop, get out of here. I keep accidentally hitting shift backspace is what's happening, and the terminal emulator is setting that as like Control H, I think. Chomp is a function from string to string. Actually, we aren't even really calling this chomp, we're just calling it strip new lines. There we go. And strip new lines equals remove equal to n. There we go. So this is kind of a fancy thing that I've done here. First of all, isn't this a wonderfully concise definition of a function to remove new lines? You just say remove equal to new line. Why does that work? This is so. Haskell does this thing called currying, which basically. Oh, god dang it! You guys needed to see this. Okay. Well, we didn't do anything very interesting. We just wrote this. I got to get the hang of switching windows again. Most of the time, when I'm recording stuff, I'm playing games, and there's only one window of interest, and so I forget that I need to switch windows. Okay, so here it is. I wrote strip new lines equals remove equal new line. Amazing, right? So Haskell does this thing called currying, which is where any function that takes more than one argument is actually like... is really... Oh gosh, this is complicated. Let me just show you a different way I could have written this. Strip new lines of S equals remove this from S. Okay, great. But remember we were talking about how the equal sign means anytime you write what's on the left, you could replace it with what's on the right, basically, right? And so while it's true that when you write strip new lines of S, you could write remove this of S, it's also true that if you wrote strip new lines, you could just write remove equals n. And so this is like something that you get out of currying, is that you can, if there's just sort of, if you have one function that just takes an input and all it does is call another function with that, you can usually sort of elide that and not mention it, and it just sort of like happens. So we do something sort of similar here. Equals n is actually the same thing as a function of x. This is how we write a lambda. Okay, actually, let's skip lambdas for a second and imagine we wrote remove. We wrote equal new line. Actually, probably better say is new line of c equals n. We could write this, and then we could say is new line. We could do that, right? But that's kind of like quite cumbersome, and so instead we could write remove lambda of c equals new line. That's a thing we could do. But Haskell lets you sort of implicitly, again, this C argument here is like kind of noisy, isn't it? It's just saying, oh, take an argument and put the argument here. And so Haskell says you don't have to write that. Equals n is a function that takes one argument and checks whether that argument is equal to n. And this is not just something for built-in operators. It's something for all operators in the language you can do this with, even ones that you define yourself. Where an operator is really just like a function that has symbols for a name. So anyway, this is like all a bit fast, and if you don't know Haskell already, sorry, it was probably a bit hard to follow. I'm doing my best, but also I don't want every video to be 6 hours long. So, you know, if you're not really following along, just sort of like bask in the glory of like, gosh, isn't it nice that we can do this? And you know what, honestly, like, why did we even define this strip new lines function? Why don't we just put it right here? That's the point of defining these things, is that once you've done it, you can replace the definition with the name anytime you like, and it's a lot nicer now, right? We just say interact, and what do we do with the string that we're reading? Well, first we remove all the new lines, then we split it into pairs, then we call part one to turn those pairs into an int, and then we show that value. Great. So, leave the REPL, please. Does this still work? No. Remove not in scope. Oh, I forgot. I'm used to working in Clojure, which has remove as a synonym for the opposite of filter, basically, but Haskell doesn't. So we can just say filter for not equals to new line, basically, right? And this should be the same thing. Aha, 1089. That's more than it was before, isn't it? It said 1080 before. Yes, there must have been two nines wrapping around the end of this thing, right? So if we look at less input.txt, yeah, it starts with a 9, it ends with a 9. Very funny. So I'm glad we checked this. the new line in our file was causing us some trouble because it was splitting up. It was coming in between the 9 at the end and the 9 at the beginning. Okay, so now we have our value. And how do I open up Chrome again? There you go. Chrome here, answer 1089. That's the right answer. You are 1 gold star closer to debugging the printer. Return to day 1. So now, after you do every part 1, they give you a part 2, which is a slight variation on part 1 usually, or a slightly harder way of doing it. You notice a progress bar that jumps to 50% completion. Apparently, the door isn't yet satisfied, but it did emit a star as encouragement. The instructions change. Now, instead of considering the next digit, it wants you to consider the digit halfway around the circular list. I see. Okay. That is, if your list contains 10 items, only include a digit in your sum if the digit 10 over 2, which is 5, steps forward matches it. Happily, your list has an even number of elements. Okay, so sadly, I did not anticipate this change. I thought that probably that we would want to split this into pairs for both parts. So I wrote pairs and then part 1. Actually, let me do something real quick. Something I like to do in these things is write a git commit for each part that I finished so I can see what the difference was between part 1 and part 2. So I'll just write yes, git commit -m day 1 part 1. Okay. So now I want to add something that solves both part 1 and part 2 to my problem, to my solution. There's no technical need to do this just for solving the solving advent of code. If I wanted, I never have to enter the part 1 input again, right? I could just, tear apart my program and change it to fit part 2. But I kind of like the idea of having a single program that solves part 1 and part 2. Okay, so there's a cool function that I'm going to use a lot in probably every advent of code thing. In control.arrow, named this crazy name 3 ampersands. I don't know why they called it that, but it's very easy to define if we wanted it to. We could say f and g equals lambda x fx gx. So it's just a way to take a single function, single value, and apply 2 different functions on it and get the result back as a tuple, which is really useful for advent of code. So I like to use this to do part 1 and part 2. So my show is usually something like this, part 2, and then the rest of the stuff. So, however, here we're going to have to take pairs out because that's actually only part of part 1. But that's no problem. We just do this, and there we go. Instead of working on p's, we work on pairs of p's. And of course, now we have to change this to string. That's fine as well. Yeah. So now we need a function that yeah, I really did not split this up in a good way. It would have been much nicer to have like this for comprehension. Take in a set of... I see. Okay, here's what we're going to do. We're going to undo all that stuff all those changes I just made. And we're going to write instead here pairs. So the first function we call is going to be pairs and then part 1. So we'll actually call this function solve now, I guess. And we'll change pairs to be, I guess, part 1. Part 1. So the idea is going to be that we have 2 functions for splitting the input list up into pairings, but then each of those will just use the generic solve function on. Actually, I guess it's fine. Doesn't matter. I was thinking it would be nice to turn the input from chars to ints before we do anything on it, but it doesn't really matter. So the question then is, how do we write part? Oh, this is yeah. Part 2 is going to be another function from string to list of pair of char and char. Part 2 of s equals zip s with something. I don't know. And so a cool thing about Haskell, by the way, is this underscore I've written here means like I don't really know what to put there. And so if we wanted to, we could do this, and Haskell will say, you left a blank spot in your definition. It has type list of char, which is the same as the type of string. And so that can, and it's like, oh, here's some strings you have lying around and ways you could maybe make strings. Like, does that help you figure out what to put there? In this case, it doesn't really help. I know sort of what to put there. But let's write zip s with drop. Let's see. Drop length s over 2. You know what? I should have another. I should just have a GHCI lying around. What is the type of this, please? It takes a fractional thing. How do you divide integers again? Div? Yeah. And what is this? Not a thing. Okay. So I actually want to name this my GHC window. So that I don't have to... Or maybe, this is my... let's get rid of this window. Forget it. What I should do is just create another GHC here. So I have one window with a shell and a GHC to look up types and things. Okay, so what we want is length s divided by 2. And these backticks mean, although div is an ordinary function, please treat it as an operator. So we're calling length of s div by 2, which is a good... We could have written instead div length of s 2, but it's kind of like traditional to put division in the middle of two things, and you can do that with these backticks in Haskell. Drop length s div 2 from cycle s, where cycle means just take the input and repeat it forever. I think that this is correct, but it's not exactly very clean. It's sort of hard to see what's going on, right? I guess it's fine. So let's see if this compiles. Oops. I guess I need to be up here now, right? And it produces two numbers, 1089 and 1156. That sounds promising, right? Sure. They're roughly the same in magnitude, but not identical. Let's see what we get. 1156. That's the right answer. You are 1 gold star closer to debugging the printer. You can return to your advent calendar. So we've done it. We've done day 1. So I was planning, by the way, to do like three problems in this first episode, But because they were very, very simple problems, I could have done this in like maybe 5-10 minutes. But I spent a lot of time explaining what Advent of Code is, what Haskell is, what I'm challenging myself to do this year, and it ended up taking a lot longer than I expected. Hopefully the next couple of days will go by in a smaller number of episodes than 5, but we'll see. Anyway, I hope you guys enjoyed. Thanks for watching, and I'll see you next time.